good day. So we are still here on our topic, external flow forced convection. So aside from the heat transfer coefficient H, it is also important to know the different surfaces where your fluid will flow. Okay, so let's start with the flat surfaces. Okay, and one of the important thing regarding this flat surface is that we must know the Reynolds number, RE. Okay, so let us consider first. Let me draw some illustration of our flat surface. Say this is our sorry for my drawing. Okay, so say this is our flat surface, and let us consider consider the parallel flow of the fluid over this flat plate or over this flat surface. So the fluid approaches this plate from x direction. Say this is our x-axis. So the fluid will approach this flat surface going to the x direction. Okay, and having the uniform upstream velocity and temperature of the fluid. Okay, so the flow at the leading edge, this is our at point x is equal to 0, starts out as the laminar flow. So if we can graph the boundary layer here, you can now see something like this. Okay, so at the start, say at this portion, the fluid flow is at laminar stage until such time that it will transition to turbulent. Okay. So the flow at the leading edge here at x is equal to 0, the flow starts out as laminar. Okay, then the transition to turbulence may occur at this downstream location at this side, at the right side of this flat surface, wherein our critical Reynolds number is achieved, right? So we say that last time we used the RE number to determine the flow of our fluid in terms of laminar, is it in transition or the flow is in turbulent. And upon reaching the critical point, or the what we call the critical Reynolds number, the flow will now become turbulent, right? Okay, so we must know the critical Reynolds number in order for us to determine what is our fluid flow. Okay, so the transition from this laminar to turbulent flow will depend on what factor. So we have different factors like the surface geometry. So what is the geometry of this flat surface? We have also need to consider the let me write it first, the geometry. Second is we need to consider the surface roughness. Yes, okay. And as we imagine, if our surface is smooth, then what can you notice about the flow of our fluid having a smooth versus to the rough surface of the of your flat surfaces, right? So the condition of your flow will depend on these different properties. Again, we have the geometry, the surface roughness, and another is regarding the upstream velocity. So it is also one of the factor, the velocity, upstream velocity, as well as we also need to consider the surface temperature. And of course, the what type of fluid is being used here. Okay, so, and among other things. And it is all of this is best characterized by having our RE, or our Reynolds number. Okay, so the local Reynolds number at a distance x from here at this point, from the leading edge of this plate, of this flat surface of this plate, can be expressed using our formula last time. Okay, we say that our upstream velocity multiplied by our what do you call this, our characteristic length over the kinematic viscosity, or it can also be equated using the density, your velocity, characteristic length, and dynamic viscosity. Okay, as you remember, we already derived this formula last time. Okay, so for flow over a flat plate, the transition from laminar at this point to turbulent at this point is usually taken occur using this critical Reynolds number, right? So using this condition, the external flow over a flat surface, our critical RE here is 5 times 10 to the 5. Yan. So this is our critical Reynolds number. Again, if our RE falls less than this value, then our flow is in laminar. And if our RE, computed RE, will exceed this value, then we say that our fluid flow now is in turbulent condition. Okay, so the value of this critical Reynolds number for a flat plate may actually vary from 10 raised to 5 to 3 times 10 raised to 6. Okay, so it actually depends on these different factors, especially depending on the what do you call this, the roughness of your surface and the turbulence level of your free stream. Okay, so once again, you need to consider this flat surface, this condition, and to know your Reynolds number. Okay, so to help us solve our H, or our heat transfer coefficient over this flat surface, then I have here some information. I have here table that correlates the convection heat transfer over a flat surface. So we have here our flow regime, the laminar, and the turbulent. Okay, so our H, or our heat transfer coefficient, we say last time that it can be divided into two, can be local or our average H. So for laminar, the of correlations of Nusselt number to Reynolds number is given here, because last time we have the formula of our Nusselt number, and it contains the coefficient, the H coefficient, and if we can relate this Nusselt number to our RE, then we can now solve the NU and then get the value of our H. Okay, so the correlation between the two is that if we have a laminar flow regime under a local heat transfer coefficient, our NU, denoted by letter X, NUX, is equal to 0.332 REX, which means raised to 1/2, and then PR, or our Prandtl number, PR raised to 1/3. So that is the correlation between the different dimensionless numbers. Okay, but we need to remember that this condition only applies if we have a Prandtl number that is greater than or equal to 0.6. Okay, so this correlation is only true if we have a Prandtl number that is greater than or equal to 0.6. Okay, so for average heat transfer coefficient for laminar flow regime, our correlation is NU bar for the denotation of the average is equal to 0.664 RE 1/2 PR 1/3. Okay, so same remarks, it must be it is only true when we have a PR value greater than or equal to 0.6. Okay, so if we have a turbulent flow regime and we need to determine the heat transfer coefficient under the local condition, then the correlation of our Nusselt number under this condition is that we have a Nusselt number is equal to 0.0296 RE 4/5 PR 1/3. Okay, and for average, NU bar is equal to 0.037 RE 4/5 Prandtl number 1/3. Okay, so also you need to remember that this condition is applicable if you have a Prandtl number of between 0.6 and 60. Okay, so that is the correlations for solving our heat transfer coefficient over a flat surface under this under the different flow regime and heat transfer coefficient, local or average. Okay. So that's all for the flat surface. Now we will discuss the cylindrical surfaces.